Hello, we represent the ASME chapter for the New York Institute of Technology, and this year we are participating in the ASME eFest Innovative Additive Manufacturing 3D Challenge. This video should hopefully give a glimpse on what we did this year, and we will be starting off with some of the essential components of the drone.
We built our quadcopter using the N3 flight controller by DJI, the DJI Snail propulsion system, a power distribution board, and the RX4R first key radio receiver. On our quadcopter, we have a power distribution board that is connected to an XT60 battery connector, and on the other end is another XT60 battery connector, but it's the opposite type. Then we have each motor soldered to the power distribution board, as well as extra 12 volt and 5 volt pins compatible with female headers, which we then use to accept a custom power distribution shield, which is capable of taking input from our RX4R radio receiver and translating it into a 5 volt 0.25 amp signal that can power the magnet, as well as the video transmitter module. The other XT60 connector goes to powering our flight controller, which controls our speed controllers through PWM wires. Our electromagnet requires 5 volts and 0.25 amps to operate. Anything more will cause it to overheat. The circuit we use to power it and turn it on and off is a solenoid circuit, but they do the same thing. The magnet only has a range of about half a centimeter from face to face. As an added safety precaution, we have a power switch going from the battery to the power distribution board, allowing us to turn off the power manually. Also, our Tyrannus controller is capable of multiple button functions, one of which we can use to remotely shut off the drone. Another form of kill switch, if you may.
For our FPV system, we chose the Fatstar Scout as our goggles, as they combine both quality and versatility. When paired with our video transmitter and antenna, we can obtain a range of more than 500 meters at the lowest power level. Lastly, our RunCam camera has a weight of only 15 grams while still being resistant to possible crashes.
When choosing the filament for our drone, we had two options: thermoplastic polyester, aka PLA filament, and stereolithography apparatus, also known as SLA filament. In the end, we agreed on PLA filament because it could help make our drone lighter and faster. Though we did not have a chance to test our drone, we would have 3D printed it with a 30% infill and 4 outer shells.
To start the additive manufacturing part off, we measured each of the technical parts like our power distribution board and so on with our handy caliper. We then started off brainstorming and then sketching different parts of the design on a whiteboard, and once we got a good idea of what we required, we created the base plate you see in front of you. The initial designs we had did not include the curves on the side, but what we noticed was we could save weight and possibly make it more aerodynamically favorable. And mixed with the fact that we didn't need the extra space, we went through and we created the curves that you see. The base plate was essentially made to hold the battery in the center, the camera to the left, and the electromagnet underneath. And the top plate you see over here was created with a similar idea in mind, but was to hold the power distribution board, the global navigation satellite system, the inertial measurement unit, and the flight controller. The arms, and I suppose the legs too, since they're connected, were to hold the speed controller and motor, in which we had two iterations of our legs or landing gear that we could alternate our designs with due to the ease of assembly we ensured when we came up with the design. As the design progressed, we had planned to create protective gear for the propellers so that it would not be able, as easily anyways, to hit and injure someone, and for it to not damage the propeller itself. though we were not able to reach a stage yet before our current circumstances. So putting all this together, you can see the assembled drone frame in front of you, and here's an animated exploded view of our assembled drone frame. With that said and shown, let's move on to our stress simulations.
Our stress simulations involved using ANSYS to see whether our design can withstand the load of the battery mainly on the base plate. Looking at the following figure, we can see that there was no dangerous bending that we had to consider. The stress of the motors on the legs were also something we had to consider. After running the simulations with the appropriate forces, we see that though there was minute bending, we could account for it by increasing the percent infill from 30% to 50% for that corresponding section, along with increasing the number of shells. Due to ANSYS not having a PLA plastic option, we chose an aluminum alloy as our next best option for our simulations, which though is a bit stronger of a material, is close enough.
In summary, each member in this team played a crucial role in each stage of the building process shown in this presentation. This team would like to thank the American Society of Mechanical Engineers for giving us the opportunity to be part of this competition. And we would like also to thank the staff and faculty and the ASME chapter for all the help and support.